the percent of annual precipitation that falls in different months. So this is January. Of all the precipitation that we receive in the year, how much of it falls in January? Right? If it was evenly distributed, the number would be 8%. Right? If we had no seasonality in precipitation, right? It just looked like same amount of precipitation every month, 8%, just for reference here. So in January, what you see here is the areas that light up in terms of the most precipitation contributing to their annual mean. It's California. Also, you'll see some pretty interesting contrasts across Washington State and Oregon, where areas basically from the Cascade Crest to the coast, January is much more important than if you get over into the eastern portion of Oregon and Washington. What is interesting about Idaho is the windward slopes of the northern Rockies. Okay, so the Idaho Panhandle. If you think about the Idaho Panhandle, I'll draw a schematic here across northern Idaho, Washington State and northern Idaho, right? So this is Seattle, Coeur d'Alene, Missoula. Right, so we might have the actually Olympic peaks, Olympic mountains. We have the Cascades, Columbia Basin, and then we have the rising slope of the northern Rockies, Bitterroot Valley, and then there's more mountains out here. But it turns out that the seasonality of precipitation on the sort of the rising slopes of the northern Rockies. So this is basically from Spokane all the way up to Milan, and in those areas, you get a lot more of your precipitation during the winter, where we have this strong westerly flow, that strong jet stream aloft. Same thing holds if we do a transect, say from, somewhere in central Oregon through the central Idaho mountains as well. There's also this uplift in topography where your westerly winds meet that uplift in topography, get the right mechanisms in place to squeeze that moisture out. Whereas if you move further eastward in the Columbia Basin here in eastern Idaho, the numbers are quite a bit less, and you can see a dramatic drop off once you get over into the lee of the northern Rockies. Okay, so that's January. Really strong in California. That's why when California gets a goose egg for January in terms of precipitation like it did this year, that hurts. It hurts. It hurts 30%. That's a 30% tax. They're not going to get that back. Here's May. Okay, again, these are all percent of annual precipitation. Peak precipitation in May is occurring actually in the northern Great Plains, right, across the Great Plains. See a little bit of, there's obviously precipitation that contributes across much of the Northwest. Obviously quite a bit more in sort of the Snake River Plain, right, than the adjacent central Idaho mountains, right? Central Idaho mountains are getting a lot more when we have strong westerly flow. Here we're talking about more convection that comes into play, strong surface heating, moisture that comes up from the Gulf of Mexico, and I'll show you that in a little bit. But where you get those two things combining, strong heating, surface moisture, you get the right sort of ingredients for convection. We still have a jet stream that actually goes through the area in the springtime. It tends to be weaker and sort of less available for the typical orographic precipitation to come into play. Okay, and you'll notice here that places like California, Arizona do not get precipitation in May. It's quite rare. This is the dry season in parts of Arizona, and it leads into their fire season, which typically starts in June and then quickly ends with the arrival of the monsoonal precipitation, which is the next piece. So this is August. Okay. Peak signature that shows up here is the desert Southwest, which can receive, in some areas, upwards of 50% of their precipitation in July and August. And this is the arrival of the North American monsoon. Same sort of feature like we talked about in sort of India and Southeast Asia. strong surface heating over much of Mexico, extending to the desert southwest. We have adjacent water, both in terms of the Gulf of Mexico, Gulf of California, and the Pacific, and that allows for this influx of flow from the ocean to the land, where they meet, where it's a warm surface, rising air, and convection. So nothing to do with the jet stream. The jet stream is, in August, is way far north. It's bringing weather systems into places like Alaska. This is all convection here. And this is also, the monsoonal precipitation is also quite variable as well. Some years can be quite incredible, and some years can be quite pathetic.
El Nino.
There are some connections with El Nino as well. So the key feature here for the monsoon is you need to have strong temperature differences between the ocean and the land, and also you need to have the right sort of lower level flow in the atmosphere. So El Nino can influence the monsoon. It also has a strong influence on the development of tropical systems in the Atlantic. And tropical systems in the Atlantic can contribute and do contribute to quite a bit of the precipitation in places like the southeastern United States. That not 100% clear that's shown here, although you do see Florida picking up substantial amounts of, more than their fair share in August than the seasonal cycle. Florida's dry season, I think, is spring. If we look at spring for much of the southeast, that's the good time of the year apparently to be there. Is that right? Maybe. You have to call it good. One of my grad students is from Georgia, and she thinks the good time of the year is in the spring. Although I'm sure she's with you on that. Places like New York, if you look at this, here's January, 8%. May, 8%. Yeah. August, 8%. It's pretty well distributed across the seasonal cycle in much of the northeast. I think their dry season tends to be in autumn for like 2 weeks. So one thing is people talk about drought. We'll talk about drought as we get into sort of the hydroclimate. Drought has different context depending on where you are. Okay, so we'll bring this all back together here. We'll look at a couple schematics of the winds at 200 millibars. We'll also look at the flow in the lower portion of the atmosphere and relate that to the seasonality of precipitation. So this is showing the wind speeds as isotachs in meters per second in the colors. The vectors are showing you the direction. This is climatology for climatological winter, December, January, February. Strong jet stream off the east coast of the continents again. Pretty much peaks out at near the date line. Weakens as it approaches the west coast. You can see the peak jet stream is maybe around 30 degrees latitude here. But it's pretty well distributed across many latitudes at this time of the year. So that's the upper troposphere. This is where the jet stream. This is where the storm track should be. So eddies should basically propagate along where we see the strongest winds typically. This is the flow in the lower portion of the atmosphere. This is about 5,000 feet elevation. So if we're thinking about the sort of flow that might interact and bring moisture into a region, we might care about what's happening at, 200 millibars, but that's way up there. That's where this jet stream is. This is more about the moisture flux into an area. So what you see here, again, you see a lot of the same features that we see at the surface, except they're quite a bit stronger. So we'll just focus on the sort of North America in general, right? Strong westerlies here. They're pretty well tied to the westerlies at upper levels. Although obviously the wind speeds tend to be a bit stronger over the oceans than over land. If you look at the direction of flow here, you see actually the direction of flow ends up being a bit from the west and southwest. So this is favorable for bringing flow or moisture in from not only a westerly direction but also a southwesterly direction. So this is helpful for bringing relatively warmer air, but milder air in wintertime into the western coast of continents, right? So that applies both here in North America, also in Europe. Whereas you look at the eastern coast, the eastern sides of the continents, 850 millibars, the winds are from the northeast. Northeast, that's bringing air mass that's been hanging out over the Arctic or the interior of the northern continents in winter. It's a terrible air mass, terribly cold, and so that's going to modify things quite a bit. They're also very dry, right? If you're an air mass that's been hanging out over, interior Canada, got no moisture in you. Okay, and this final plot here is total precipitable water. I think we talked about this, right? This is if we look at the atmosphere, we squeeze all the moisture out from the surface to the top of the atmosphere, measure it, how much water we would have. And what you can see here is obviously quite a bit in the tropics where we have more moist air. If you look at the gradient across the Pacific here, you'll actually see that in the wintertime we actually have high amounts of precipitable water that come into the northeastern portion of the Pacific, and also same thing with the Atlantic. So that's going to be important if we combine these two features together. This is the moisture flux in lower levels of the atmosphere. Here's how much moisture in the lower levels of the atmosphere. You put those things together with the jet stream, and that's responsible for the abundance of precipitation that we receive in the wintertime. Okay. Here's summer. Here's the jet stream in summertime, right? Much, much weaker, much further north. There actually ends up being this branching of the jet stream. You can see sort of two regions of maxima, one maybe near Hawaii, one much further north. This is in a climatological sense, at least. Here's the lower level flow in summer. So what you see here, if you look over the Pacific Basin, you see this clockwise circulation, right? So that's basically the manifestation of the subtropical the Pacific high, right? So that's bringing air from sort of the northwest down along the west coast of North America. It's cooler air. It's got the right sort of characteristics to be stable as well. East coast, here's our Bermuda high. It's bringing air across the Atlantic, warm air, and moving that northward. And then also notice this feature right here, right? And this is bringing low-level air that's been hanging out in the Caribbean, Gulf of Mexico, very, very warm. And it's a southerly jet, so it's bringing warm, moist air up into the midsection of the country. And when that meets the warm surface temperatures that you get in July in Kansas, or in June in Kansas, got the right sort of ingredients for convection. Right? This also occurs earlier. Actually, it would also exist in like May if we looked at May. So this low-level jet is responsible for bringing that moisture into the region. That's why we see this precipitation maxima in the north, sort of the Great Plains in late spring into summer. And precipitable water, of course. So high amounts of precipitable water, right, over the Caribbean. And now that's all this mugginess that you guys experience on the East Coast. Whereas here at the West Coast, we have relatively low amounts of precipitable water. In fact, if you look at how low it is basically you look at the values, and my mouse is gone. Oh, there it is. The values we see here in the interior West, precipitable water, compare that to other locations, it's pretty much the lowest we see for that latitude in the summertime. So moisture starved, if you will. Part of that has to do with topography too. So if your elevation of your topography is already 5,000 feet above sea level, it's just that much less moisture you're going to get. So I think this is a good place to end.